Hi everyone, we are live. Um, in this stream I would like to show example how to configure application, simple application in C++ that will use Intel Intrinsics instructions and Nvidia CUDA. That will be show and tell, and yeah, we will make an end break probably. So let me start. For that we need Visual Studio Code and actually free tools. So I will show it. So we will need CMake. So on my platform I use Linux. So I have CMake in that version. You can download that from Kiteware, and this is tool to build the whole application. It manages configurations and the steps to compile, assembly, and the linking of the libraries. So we will use at least CUDA runtime for that, and we will use Intel compiler. So we need to have them installed, and please follow additional instructions. So for Intel we need Intel compiler. If you type in Google Intel compiler, that will be one API, DP C++ compiler, and you have to go to, actually I have HPC toolkit, and going to download. You need to register actually to download it, and you need to choose your operating system. So you see here what capabilities and what library it has. For now, let's use just the compiler actually with Intel Intrinsics instructions, but there is much more from this package. Yeah, so you can find here, and actually I already have it, so I can check that. Where is ICX? Where is ICX? I have installed it in my home catalog. That's under that path, and actually we will need to know a bit about that path, because we need also to have information about the includes of C++ from the compiler. Another one is Nvidia CUDA. So if you type Nvidia CUDA, you will go directly to Nvidia developers and developer site, and from there you can also easily download that. And where is it? Okay, so probably you also need to log in. If not, then you can just pick your version of your distribution. So I have Ubuntu 2404, and you can download as run file or daemon package. There are instructions. I will not be going through that instructions. So you need to check. Also be aware about the version 12.6. So for example, this is not the version that is supported yet for by PyTorch. So we need to wait a bit, or you need to compile the PyTorch on your own if you use it. Okay, and CMake, there is CMake.org. But you can easily install it with apt, but you have the documentation there and other resources that you can check. Okay, so where is CUDA? Where is CUDA? So CUDA is under user local CUDA, and actually you need to update your .bashrc and have in path, you need to have the binaries linked, so just you can use the compilers from path if you will be checking manually, but for this application we'll use CMake configuration. Okay, I can close it. So there is workspace prepare for stream number 1, and we can open the terminal, and actually we can start. We can start with creating the files that we will use. So firstly we use CMake lists txt, and we will prepare the CMake minimum required. Also I have the plugins for CMake for C++, so that will help to streamline the configuration. Version. So let's have the minimum is 3.10, and let's create the project. That will be CUDA C++ project. First we define the languages, and let's start with the host. So we just create for C++. Okay, and we set the compiler flags. So there we have defined, and we will use the optimization and architecture that will be native. So this is for the host, so for Intel, and you can check your Intel with LSPCY, so host bridge. And you can check with CPU info, where you can check also the instructions that are supported. And for this example, we will be using advanced vector extensions, and we have the of FOX2, but we will use also FOX15. So 2 is for 32 bits, sorry, vectors. Okay, but firstly, okay, we have Intel Core, and there is 8 threads, 8 siblings, so 8 threads that can run in parallel. But this is not about the multi-threading, it's about Intel Intrinsics. So we use the instructions that that are run in the CPU and are some addition to the multi-threading applications. So you can create multiple threads, but from the threads you can also utilize the Intrinsics instructions. Okay, and for now let's create another file which will be main CPP, and we will use, of course, IO stream for now, and let's define our main function. So this is the main thread, and return 0. Okay, let's we have that one, and we can just compile with G++. Compile main, and output will be, we just compile, and then we will link to cannot find. Oh, sorry. Not correct. Okay, we have but it's not doing anything. So let me remove main dash. Yes. So for first, let's create now the header file that will link additional file with intrinsic functions. So let's define if not def header.h. Let's define header and if so actually that prevents from multiple includes if you will use header in multiple files, so the compiler will use it just once. And let's create the declaration of the function. It will be process data, and it will be the declaration of the function using Intrinsics. Now we can include that. Include header. Yeah. So one more step is to create Intrinsics CPP, and our Intrinsics will include string to print some informations, and we will include IMM Intrinsics. And currently that IMM Intrinsics points to GCC, where there are includes to all instructions that are supported, but we will use ICX. So for that we need to create configuration, for our workspace, and there in include path we need to add catalog with the includes. So just one second. So I'm looking for the catalog. So we have home Intel 1 API compiler, latest which point to the 2025, and then we have so not includes libraries, and there are so this is the correct. So copy that, and then we can include that catalog, and then sorry, compiler and clang. Okay, so this is the correct one. So currently we have yes Intel 1 API instructions. So there are definitions, and it uses the Intel registers, and CMake will actually handle the compiler we use, and it will link the libraries properly for us. Okay, so for Intrinsics, we will compile with the header. So in the header, actually there is that function, and we need to define function. We don't need to put header here because it will be used within the CMake. So let's define firstly. We will use simple instructions to multiply two variables, but using the AVX 512 instructions. So let's define the number we'll use for that. BS size n equal 16. So actually we meant here 16 digits. Actually 16 single precision floating point numbers, and there will be example x 95 intrinsics. So we define 1, 2 number A, which will be 1, 2, 5 set 1 single precision, let's say number 3. So that is our first variable. Will be A. We'll copy that. We'll use number 8 for our B variable. So that will be set on 16 floats to 3.0. and with same latency calculation, so it will be like, it is SIMD, so single instruction multiple data, but simple example as I mentioned. So in one instruction we calculate multiple data, and we will have 512, that will be C, and for that we'll use 512 so single precision A times B. Okay, so we have it, and we'll handle the result in the float that will be array of 16 floats. So we have it on the stack, and then we have additional instruction 512 store PS, that is our rest, and we want to store our rest from the C. And let's print five one two for that let's print result of I, and then at the end with end line. Yeah, so this is just simple example and starter for using the Intrinsics to take more from the CPU. So as I mentioned, this is not about the multi-threading. That's Intrinsics in using one thread of our CPU, but from that thread we use additional registers and SIMD operations to streamline actually the vector processing in one instruction with one of latency of one instruction, just not multiple instructions like in the loops or other ways. Okay, so we have it. So we can back to our CMake, and we can set our sources. Set sources, and that will be my main CPP, and in Intrinsics CPP. Hope there is no typo, and we need to define executable. Executable will be up from our sources. Okay. but also we need to update our main because we have nothing here. So from main, so firstly we type, of course, hello world C++, and then copy that instruction and then show enter intrinsics, and we'll just call process data. Okay, and for that we need to create our folder. We can go to the build and okay, so we need to call CMake success compiler ICX and point to the upper folder. Sources, okay, we have some error, no sources. No sources. Yeah, so that was built. Actually not built, but it was prepared. So we have the configuration done, and in our build we have the make file. So now we can call make. Oh, and we have some issue. Okay, so it's FOX 512F. It was not enabled. So for that we use attribute target. This is X 512 BW, and this is the information for the compiler. Wow. Undefined reference to CMD, to standard cout. Process data. There is IO stream. Okay, so let's standard cout. That's interesting. That's something new, actually. So, have I defined it properly? Have the attribute. if I leave it on, call down. We don't need that. So what is the problem actually? Header. X 512 BW target. Okay, but if we compile manually, and then if we link that, again, same issue. Standard C out. And define the first. How it's possible? IO string. Okay. There is C out, obviously. What will happen if I delete that? Okay, let's use previous instructions. CMake. It won't compile. Again. have problem and I don't know now how to solve it. Main. Okay, if I will comment that, in main now. C++ 13. Okay, so if I will use G++, so with G++ that works, but that was not the topic. And it's not working there. And executable. Main CPP. Intrinsics CPP. Sources. Target. Link libraries. Does it change anything? I don't think anything, so standard C out. And okay, if I will use, let's say, printf, and then printf. Okay, now it works. So I need to work on that to use IO streams from C++. So there is some problem with link library. For example, I was preparing, it was working. I had other issues, but that was working. But yeah. So for next stream, I will take same example, and let's say we will use always same example, but with some updates, upgrades. So there will be iterations and incrementations on that example exactly. So for next steps, for next stream also let's prepare the version with IO streams and C++ linkage. But we see it's starting to work. Maybe over there we need to put new line. Okay, so we see that 3 times 8 is 24, and actually it calculates multiplication for all 16 numbers. So we have 512 bits multiplied by 2 because it's single precision, so we have 4 bytes. So it is 16 4 bytes in one instruction latency on the CPU. Okay, so let's say with issues as always, we have FAOX 512 instruction that is working properly with standard input-output. So there is some progress and some lesson learned on that. And currently, let's switch maybe for a moment to Nvidia CUDA and how to operate the same. So we will add to that example Nvidia CUDA operation to do some additions on the grid. Means from our computer, which is called the host, we will use the device, which is GPU, and we will pass information. So the host is CPU with its RAM memory, and we have device, which is GPU, which is a DRAM memory. So I will not go into very details of the CUDA, but let's prepare just working example, and with other streams on the YouTube in the iteration and implementation process we will build more from that example with some additions and probably some other issues, but hopefully we will be starting to utilize high performance computations. So I will just check one thing. I will add thread, read, compile, and if I will print, let's print %d of thread hardware concurrency. Let's see how many threads we can run. Threads number, yes. Undefined reference. Okay, so there is some issue with the compiler and the link libraries. Oh. No. So one more. Okay, so the issue is about the includes. This is our C++ 13 thread, and the compiler we are using is ICX. Okay, I'll stop for a moment. So something that will be an additional stream regarding how to fix that issues. But let's go to Nvidia CUDA current. Yes, so we need to define additional method for the CUDA. Let's say it will be process CUDA data, and that is declaration of CUDA kernel function. So not CUDA kernel, CUDA function that's called CUDA kernel function. I need to create one more file. Let's call it CUDA.cu, and CUDA.cu extension cu means it will be CUDA file, and here we need to include CUDA runtime. CUDA runtime, okay, we have under user local CUDA targets, so the functions declarations are there. And what we need, just for beginning, simple example, the global attribute, let's it is information that is CUDA kernel, means the function that is called by the host and it's run on the device, means on the GPU. Hello, and let's set be printf as well. So we need to put IO stream, have input IO stream, have printf there. Okay, and this is information hello from CUDA kernel. Just simple example, and we need to define what we declare. So this is our function, and our function just will create hello kernel. We are using such construct, and we mentioned there the block size and thread size. So kernel you need to have information about the number of blocks and number of threads per blocks. So this is our grid actually, and this is just one block and one thread, so we will just run one thread on the GPU. And that's it. This is the first example. We do second example, if that will work. And we need now to synchronize CUDA device synchronize. So that will block until the device is complete all preceding request tasks. So we will return from that function when the kernel on the GPU ends. So that function will wait until the task is completed, and there will be a second task number 2, but we will define it soon. And we need to go back to CMake configuration file. In the CMake we need to add our languages. To CXX we add CUDA, and then we need to add libraries, link libraries with CUDA library, and we need to set CUDA architectures. CUDA architectures, it's what we have, so what GPU we have and what CUDA version it support. And I was checking that and you can check as well SMI, so we use that function and we see that we have CUDA 12.6, and for the version we can see what GPU we have on the board, and this is Nvidia GeForce GTX 1050. And for that platform we need to specify target properties for our application. This CUDA architectures, and then we set to supported 72. You can Google more on that, what architecture, but you need to pair with your GPU. So that was working, and I hope it will work as well. So let's create project again. I don't need that. We don't need that. Okay, and from main it's called CUDA kernel. We call it for our function, which is process CUDA data. Okay, that's clear. Terminal. Let's use previous. Okay, and let's make undefined reference, it is CUDA. Oh, because we need to add our file. Okay, if we run hello from CUDA kernel. Okay, so our kernel run on the GPU, and now we can go to more advanced example that will do vector addition. And the task will be more complicated. So firstly we need to add task number 2, and we'll call from here task number 2, and our task number 2 require additional kernel. That will be vector addition, and we will pass pointers to array of floats A, pointer to array of floats called B, and pointer to our result will be C, and by value number of data we are passing. And add void there, and there we use the constructs to for our index, and that will be block dimension. That will be 3 dimensions, but we use 1 dimension, that is x time block x, and plus thread idx of x. So this is information how many threads for the block we are calculating. So as you saw, there is like 3-dimensional construct to run the grid actually, and this is mainly based on the architecture of the GPU processor. And until so that function will run on the grid utilizing the block of threads, and we will just run the n calculations and threads. So then we will stop. So for C of I, we need to add A of I plus B of I. So for that you need to go through the CUDA. I will not be mentioned tomorrow because maybe I will be lying. So let's wait, and with the incrementation and iterations we will go deeper into how the GPU is organized and how to utilize most of it. But currently we need to know. Also, that example is taken from Nvidia website. So I will just run together the example of Intrinsics and Nvidia CUDA just to have a brief of how to run it, how to build the application, and what potential issues are like with the C++ includes for the libraries. Okay, so let's define number n, what will be 100 numbers, so 100 additions, and we need to define the size, our tables for the memory on the host. So that will be size, and we will use n times size of float. So it will be 100 times 400 bytes will be reserved. And then we need to allocate vectors on host. So we need to define float host A. It will be malloc. So on the free store, on the heap, and we will return pointer to float. What's the issues there? Because we don't have the pointer there. let's copy that and let's allocate the other two for B and for C, and let's use memory set to set the values, and for HC we set that to 0. But that's quite useful function to set all table with the 0 value. But we need to initialize A and B. A and B. For that we use loop I less than I plus plus, and we will define our H A of I. It will be 1 plus I, and for H B of I we will use 100 plus I. And so this is our entry point, and then we need to define the device variables. Float. So our pointer to floats, and with CUDA malloc take the first element and D of A, enter the pointer, size, B and C, B and C. So we will reserve memory on the device. Device memory means GPU. And then we need to copy our host values, host data to device data. For that we do copy vectors from host memory to device memory, and that is CUDA mem set. CUDA mem set, and one is the device pointer, device A, host A, the size, and what we are doing. So CUDA mem C, mem CPI, host to device. CUDA mem copy. Size. And the same for B. B and host B, device B, host B, destination memory, source memory, size of bytes to copy, and type of transfer. So that's the function. And then we need to invoke kernel. There is really that is disturbing a bit. Int threads per block, as I mentioned, that will be n threads and blocks per grid. blocks per grid, and for that we use the formula n plus, actually it will be 1, but let's do it properly. Threads per block minus 1 divided by threads per block, and we call our kernel function, so right, and we put there blocks per grid, threads per block, and we are passing the A, the B, the C, and the number. So as we define it. Okay, and then we need to do reverse copy from device to the host. memcpy host C, device C, size, and type of transfer, so it will be CUDA memcpy device. You can also do device to device, but we don't have more devices. Device to host. So our data will be stored in h_c. So now we can free device memory. So CUDA free I don't need any of it after the calculation, so we need to free it to be used by other processes, B, and as well C, because we have copied to HC. And then we can print data, and then we can free host memory with simple free HIDHC B, and for print let's use printf. I'm not sure why that workspace standard library doesn't work. I will be checking that, and in next stream we will go to more advanced examples of standard libraries as well. So for and we use printf to print float, and that will be HC of I, and just at the end print new line. Okay, if we make it, okay, it will build our CUDA without problems, and if we run from CUDA, but we don't have there. Okay, let's add at least space. It works. Looks it works at least. So we start from 0 and we are adding from 0 to 100 and from 100 to 200. So the calculation works well. So firstly we have intrinsics operation on the vector, and then we have the CUDA kernel that is also printing the correct values. +1, okay. If we start from 0, yeah. So actually there were some struggling and there are always struggling, always new lessons. I hope you've enjoyed it and you saw how to build a bit advanced application that utilize Intel Intrinsics, Intel compilator and Nvidia CUDA. So yeah, there will be more streams, and for sure it will go better than the first one, and we will have some surprises. Okay, thank you and see you later. Cheers.